to start out by thanking the Livermore National Lab for offering Science on Saturday again this year. We've just learned that this is its 14th year. Goodness. And we're pleased to be here at the Bankhead Theater. For veterans of early sessions of Science on Saturday, they may come to know what Livermore has already discovered. Everything is better at the Bankhead. And science is so important to everyone. Many school districts have special programs to make sure that their students get science instruction from teachers who have a love and a passion for it. In Livermore, voters approved a parcel tax a couple of years ago to make sure that our elementary science program was kept intact. And we are so very grateful to the Livermore Lab as it continues to step up and offer this important enrichment program to the student in its neighborhood. But why is science so important? Why is it so important to ruin a perfectly good Saturday to hear about it? No one offers algebra on Saturdays. Whether you do science as a career, a hobby, or just study up for an occasional ballot proposition, science is a part of our everyday lives, even personally. When your physician offers you a choice of treatments for your ailment, you must know life science just to know what she's talking about, to ask important questions, and to make an informed, careful decision. But what's the science for this Saturday? Geothermal energy, earth heating the heat beneath your feet. There is certainly more to it than volcanoes. Today we have several presenters. Carol Bruton is a senior research scientist at Lawrence Lab. She's worked there for just over 20 years, and the last 10 she's concentrated in geothermal research. Before coming to Livermore, she worked at Arco Oil and Gas Company, and to prepare for all this, she earned a PhD in inorganic geochemistry at UC Berkeley. At the lab, Carol works to develop geothermal resources and provide technical assistance to the geothermal industry. Ken Waddell not only teaches Tracy High School students earth science, but he developed the earth science curriculum, making sure that it was matched to the California State Science Content Standards. There must be a set of initials for that. He's part of a team of master teachers that are working to develop an environmental science curriculum at the lab. Ken coaches the Science Olympiad team in Tracy and works regionally with the Olympiad program. He earned a Bachelor of Science degree in geology from Cal State Stanislaus. In his personal time, Ken does earth science by backpacking in the Sierra and exploring national parks with his family. His children are learning that rocks are cool. We will also hear from John Ziagos, a senior scientist in the Atmospheric Earth and Energy Division at the lab. His PhD is in geothermal studies. He made the first geothermal measurements in central Mexico in 1978. That was 30 years ago. John leads the team which is developing the environmental science curriculum. Now it's time for Carol and Ken and John to tell us about geothermal energy, harnessing the heat beneath your feet.
Thank you, Ann. Well, I wanted to thank you all for being here today. It gives me the opportunity to tell you about something that I'm really passionate about, geothermal energy, because it involves so many interesting scientific and engineering opportunities and challenges, and also because it's socially relevant, because it's a renewable, clean, green energy source that can really play an important role in our nation's energy future. What you'll be talking about today, we'll sort of be reviewing the whole thing about geothermal energy, where it comes from, what is it, how does it get to the crust, how is it used today, and where is it? Focusing on the world, but especially on the US and resources here in California. Finally, why it's good to use geothermal energy, and finally, what does the future of geothermal energy hold for our energy in the United States? Now, geothermal energy. You walked in today, you didn't feel it under your feet actually, but it's down there. And we have clues all the time. And that's because you see things like volcanoes, Mount St. Helens. We have hot springs. We have lava fountains. This is Kilauea in Hawaii. The volcanoes, lava comes up, shoots up. A lot of energy, lots of heat. Yellowstone National Park, geysers all over the place. That's illustrating the source of the heat that we may not see on the surface, but it's coming from deep below. Now, what produces this heat? I mean, there's tons of it out there, and you've probably seen this in your geology or science classes. The source of the geothermal energy is the heat of the Earth, and a lot of the heat of the Earth came back from when it first formed. You know, when the Earth first formed billions of years ago, it was this almost a cloud of liquid and gas, and then it was getting showered by meteorites, and these meteorites were transferring their heat and the mass to the Earth. Well, as the Earth started to cool, become condensed and solidify, the heavier elements, like iron, went to the center of the Earth, to the core, and with this whole, just the contraction of the Earth, this gravitational sinking, added heat to the Earth. So, but there was another important thing that happened. As the heavy elements were sinking to the core, the lighter elements, the element and the components that are rich in radioactivity, were coming to the surface of the Earth and concentrating themselves in the upper mantle in the crust. This natural radioactivity comes from elements such as uranium, thorium, and potassium, and they're really concentrated in the rocks in the Earth's crust. You look at the crust of the Earth, and it's only like 1% of the total volume of the Earth, but it has a tremendous quantity of these radioactive elements. Now, these radioactive elements, you know about radioactivity. In a radioactive element, the nucleus is unstable. So over time, the nucleus will fall off these little particles. And as it falls off the particles run into particles right next to them, and it generates heat. And this natural radioactivity occurs in most of the rocks in the crust. And Ken can demonstrate on a rock from the Sierra Nevada this natural radioactivity. Not much. You hear the beeps? That's signaling that it's picking up some of this decay in the rock. And this is a rock that's 80 million to 200 million years old. And that's the content: uranium, thorium, potassium, the radioactive elements that are contained in that rock. Thank you. It's this natural radioactivity that means that we can go to the Sierra Nevada, as we see here in this picture, and we get hot springs. Now this mountain range is, say it's 100 million years old, very old, but because these radioactive elements have half-lives of billions of years, they keep supplying Earth to the Earth's crust. And that's what we're going to tap into for geothermal energy. Now heat is a measure. We can look at the temperature as we go deeper in the Earth, and the temperature as we get down the Earth is a measure of the heat content. So if we go down about 3 kilometers in the Earth, we can see the temperatures are about 50 to 100 degrees C, pretty good throughout the US. But notice as we go deeper, 3 kilometers, 6 kilometers, 10 kilometers, the temperatures gradually increase due to this radioactivity of the rocks. Now you might notice something interesting. Now by the time you get down to like 10 kilometers, about 6.6 miles, the temperatures get up anywhere from 200 to 300 degrees C in the west coast, but they're not quite as hot on the east coast. Now why is that? That reflects how the heat in the Earth is brought to the surface. And that brings us to plate tectonics. Now you might know that the Earth's surface, the crust is pretty thin in the Earth, about 5 to 35 kilometers thick. But that's broken up into these plates, which are constantly moving relative to one another. And on this diagram here, these yellow boundaries here show these plates, the edges of the plates. Like this is the Pacific plate, which borders up to California. Now look at the volcanoes. These red triangles here represent the historical eruption of volcanoes, and they border the plates. These borders of the plates are where most of the geothermal energy is produced at this point. And that's because things like the Ring of Fire. This is known because the Ring of Fire, it's a Pacific plate and some plates around it, highly active in volcanoes. And these volcanoes are where traditionally we've produced most of our geothermal energy. You can see this ring of fire, the west coast of the United States. That's where all our energy is coming from. But how does heat get up there? Okay, yeah, we've measured the temperatures. That gets us to the mantle and convection. The heat gets up to the surface of the Earth because the mantle, which is partially liquid, is convecting. Basically, you know, the mantle, it's high temperature at the bottom, colder on top. So what happens when you're hotter, you're less dense, the mantle tends to rise. But as it rises, it cools off, gets denser again, gets to sink. So we get these convection cells in the mantle. Sometimes it breaks through the crust, and you get these mid-ocean ridges, and you get magma right up the surface. Sometimes all it does, it moves the plates and subducts one plate. You know, but these plates are moving around, right? Well, sometimes one starts ducking under the other because there's no, if it's being spread apart here, it's got to go someplace else. So it spreads, and at the other end of the plate, it ducks under the other one. Well, as it starts subducting, it increases in temperature again and eventually melts. And this is magma from this subducting plate that forms this magma chamber. And when this magma chamber erupts, then we get our volcano eruptions, and the magma becomes lava at the surface. And actually, for all the lava that we see on the surface of the Earth, there's about 10 times more volume of magma underneath the surface of the Earth. And that's what we want to tap into to get its heat out for geothermal energy. Now, this whole process of convection is something that we're going to be coming again and again to for geothermal energy. So Ken now has a demonstration of what convection is.
Convection can happen in any substance that can flow. So water can flow, air can flow, and magma also flows. Since I'm not going to have magma on my table up here, I'm going to use air to demonstrate convection. What's going to happen is I'll light this little paper on fire here, and the fire, like the Earth's core, will heat the air above it, or the core heats the magma. Then what will happen is that air will then rise because it's less dense. At the end here, the paper will follow the air so you can see that its path and show that the air is rising. Everybody find their safety exits? So that flame is producing a column of hot air which is rising up. We can't see it, that's why we'll use the ash as a marker. So the ash followed that hot air up. It's rising. When it gets up there, it will lose its heat and then come back down again like convection in the mantle.
So now we've got convection in the mantle to bringing heat up to the bottom of the crust. But how do we get that heat in the mantle up to the crust, the upper 35 kilometers of crust? Well, again, we look upon convection and we use conduction. Now, the thing about the crust, it has a lot of water in it, you know, groundwater resources. And so this heat from the bottom of the crust causes convection in the fluids. If you look at the cross-section of the schematic of the cross-section of the Earth, most of the fluid in geothermal systems in the Earth actually started as meteoric water, cold precipitation that rained down on these recharge areas. Now, when it rains on the surface, it tends to recharge, drop down, and go into the underlying rock units, and it's cold. But as it percolates down into the ground and gets closer to the source of heat, starts heating up again. And here we go with the convection cycle again. It gets hot and then starts convecting. Now for a geothermal system, what we're looking for is we want to capture that heat. And what's important is that we have this impermeable cap rock on top of it because it captures that heat underneath that layer. And we see indications of that sometimes when we have hot springs. When we have fractures going through that cap rock, we may see the indication of that geothermal heat at top, below when we get a hot spring. So now, the three components of a geothermal reservoir this is basically a geothermal reservoir. Hot fluids moving through permeable rock. We need three things for geothermal reservoir. We need the source of the heat, which we get from below, the nature of Earth. We need a source of a material to pick up that heat, which we can extract from the rocks, and that's water. So the water goes through the rocks, picks up the heat. Now, we also need another thing, it's called permeability, which is related to porosity. Now, porosity is simply the pore spaces in the rock. Like if you were to fill this glass jar with these beads, these marbles, you know, the empty spaces between these marbles would be the porosity, and this is filled with water. But for a geothermal system, what we need to do is be able to move the water through the rock, through these pore spaces, and that's a measure of permeability. So for geothermal reservoir, we need three properties. We need the source of heat, we need water to pick up the heat from the rock, which we can then extract, and then permeability, which allows the water to move through the rock. And now Ken's going to demonstrate his reservoir simulator, this geothermal reservoir.
So if you have a heat source from the core of the Earth, that's going to heat the bottom. And between all this rock down here are pore spaces. Pore spaces are small air pockets in the rocks. Some rocks can have up to 25% air pockets. And when those are connected, that's when you have the permeability where water can flow through. So if you have a heat source on the bottom, you can tap into that. So I'm going to take some red dye and we'll inject it down one of the wells here to show where the heat source is. So you have a heat source at the bottom simulated by the red dye. So when a geothermal plant wants to access that, you have rock that is not permeable. That would be the dark layer. And that dark layer doesn't have any pore space. So if you have a well that doesn't reach there, you can draw water out, but you're not tapping into the hot water that you need. What you have to do is, to be able to tap into the hot water that you need, is have a well that also goes down into that geothermal reservoir. And then you can tap in and draw that hot water up into the plant. And then the plant can use that to create the electricity. What also happens, if you continually draw water out, your reservoir then will drain. So what the plant will do is, after they use that water, they take and inject it back into the reservoir to replenish it. So that way the system's complete.
Excellent. And this is a great example of how a geothermal reservoir works and how we produce it. As we're taking out the hot water here, we're making sure to always put in an extra source of cold water, which will then heat up. And then as we're drawing this water out, it's going to gradually move over to the production well and heat up. And that is our heat carrier. So water is essential because that's our heat carrier in the system. So basically, this is an illustration of what Ken was just showing there. We've got our components. We've got our rainwater is our source of fresh water. It comes in, it's cold, it goes down, it gets heated up and starts circulating. Okay, so all we need to do now, is drill down to get it out. So these resources may be pretty deep in the earth. They may be as shallow as 500 meters down, but they could be as much as 10,000, 20,000 feet down, equivalent to where oil and gas wells are drilled today. So what we do is have these huge drilling rigs to drill down to these depths, and it's great. They use these bits to grind the rock and form these cores. And here's an actual example of a core from a well that we collected of a granitic type rock. Okay, so we got heat in the earth. We know how it gets through the mantle, and then through the convection in the mantle, and then when it gets it to the bottom of the crust, then water distributes it through the crust. Okay, once we found a reservoir, we drill down to extract it. Now, how do we get power out of this? How do we convert this thermal energy to electricity? And what's curious is that the way we use geothermal energy, geothermal heat to produce electricity, is the same way that fossil-fueled plants like natural gas or coal-fired or nuclear power plants produce electricity. They have to use another source of heat to create steam. Hey, we've got hot water. Our hot water at depth is under high temperatures and pressures. When we bring that hot water to the surface, we reduce the pressure. And what happens is the water boils, or as we call it in the industry, it flashes. It's a much more exciting word. So this hot water, when we bring it to the surface, we reduce the pressure, and it flashes to produce steam. Well, steam has about 1,000 times the volume of water. So it tries to expand, but what we do is we have it in a restricted flash vessel. So we control the space. It doesn't have much space to expand, and we only let it escape through these high-pressure nozzles. So what happens is steam comes shooting out of these nozzles to hit a turbine, and it shoots out at up to like 450 miles per hour. Well, when that shoots a turbine is basically a rotor with a bunch of blades on it. So the steam hits those blades and turns the turbine, which then turns a generator and creates electricity. Now we can look at that in a little more detail in the next slide, because what we see, the turbine has many blades. The turbines are huge. I mean, they're like twice my height. Twice my height. And so it's attached to the rotor. So when the steam turns the turbine, which turns the rotor, which turns the electrical copper wire, which is inside a magnet, and this produces electricity. It's electromagnetic induction. And Ken has an illustration of this production of electricity.
So that steam is hitting that turbine and it's spinning it. So we have a spinning motion. Just like my hand, I can spin this little device here. Now I can spin all I want, and I'm not going to heat up a bulb because these coils have to be within a magnetic field. So I put my magnet on, and then when I spin it, my belt comes off.
That's called a plant upset. You see. There we go.
So the bulb is lighting up here. And of course, the faster I spin it, the more electricity it creates. I have to go fast to get it to light a lot. So it's with the magnet and the coil spinning that creates that.
So what we've just seen is we have heat energy that was converted into mechanical energy, the spinning of the turbine, which was then converted into electrical energy. And that's how we use thermal heat, geothermal heat, to produce electricity. Now sometimes, if you remember in one of the earlier view graphs, remember we saw the picture of the US, and in the western US we had high temperatures above 200 degrees C, but in the eastern US it wasn't quite so hot, where temperatures were like 50 to 150 degrees C. Well, we can still produce electricity from those fields, but in a little bit different way. In those fields, the water we bring up from depth isn't quite hot enough to flash to steam as we bring it up. Okay, so if we don't have that steam that way, let's use another fluid. Let's use a second working fluid. That's why it's called a binary system. As we bring the fluid up from the surface, we send it to a heat exchanger, and there, through conduction, the water transfers its heat to a second fluid, which is usually like an alcohol, which boils at a lower temperature than water. So the hot water heats up the secondary fluid, and that boils. And so then you take that gas and send it through your turbine, and it creates electricity in the same way. Now, so what we're using in the heat exchanger there is the principle of conduction, which Ken can demonstrate.
So normally, water boils at 100 Celsius. My hand can't produce enough heat, just like the water coming up cannot produce enough heat. So what I can do then is use my hand's heat by conduction, will hit the molecules in the glass, transfer to the liquid inside, and since it can boil at a lower temperature, it can then turn it to the steam that we need. Just means I have warm hands. So that way you're then creating the steam that you need even though you don't have the temperature in the geothermal reservoir to start with.
Thank you. So there's all these ways we can create electricity from hot waters of different temperatures. So I think we've given you the cycle now. You said the Earth's hot, you know why, you know how heat is transferred, and you see how we access it. Now, the next challenge is our Earth requires a lot of energy, and we want to be able to produce geothermal energy from areas that aren't related to volcanoes. But the trouble is if we don't have a volcano there or a hot spring to tell us where the resource is at depth, how are we going to find it? Because these resources, I was saying, could be 1 to 2 miles below the surface of the Earth. And if we have no surface indicator, how are we going to find it? What clues does the Earth give us? And that's one of the areas that the Lawrence Livermore National Lab is working on, remote sensing techniques for exploring for these hidden systems. And I'll tell you about one of the projects that we have, and that's using satellites. Satellites that contain radar. And what are we looking for on the surface? Well, down below in a geothermal system, we found that most geothermal systems exist where you have a lot of fracturing, where there's a lot of forces in the rock that's creating the fractures in the rock and movement and creating permeability. Now, we can't see that down below, but sometimes those displacements are actually transferred to the surface of the Earth. So instead of getting major displacements 2 miles down, we may be able to see the surface of the Earth flex, only maybe perhaps millimeters per year. But we're looking for that slight deformation in the Earth's surface that may indicate we have deformation below, which is creating a geothermal system. So what we do is use satellites. Now, these satellites contain radar. And when they take a pass over the Earth, they shoot an image of the Earth and they collect the echoes from the radar. And then they take another pass in the satellite and they compare the phases of that echo from one pass to the other. And we're not going to get into the details, but geophysicists process the data and they can actually use this radar to make a map of the surface displacement. And that's what I've shown on the bottom here. They're a little bit fuzzy, but this is a map. This is Nevada here, and this is the Nevada-California border. Here's Lake Tahoe right here. And this is the track of a satellite. These are all tracks of satellites. And we've taken these scenes, and these are big scenes. These are like over 100 kilometers square scenes. And that's especially why remote sensing is good, because we don't have enough geologists to walk across every inch of the Earth's surface looking for geothermal resources. Let's go use satellites and view huge swaths of the Earth's surface at one time. So we take these satellite images and create these maps of deformation, and these colors on these maps represent the flexing of the surface in millimeters per year. So if we see an area with these bright colors, we would then say, okay, we got to look at that, we got to go send a geologist on the ground and use some other exploration tools in that other to look for the resource. Or maybe even just go ahead and drill an exploration well right there. So this whole concept of stress-creating fractures is going to be illustrated by Ken.
Different forces create those. We talked about plate tectonics earlier, how that rising magma can move the place around. So a lot of times that movement can't be seen underneath or on the surface, what's happening underneath. So here we'll create some compressional forces that will cause deformation in the Earth. So you have an offset where you know there's deformation and probably the cracks and fractures necessary for our geothermal plant. But on the surface up here, you can't see it, or sometimes erosion moves it so it's not visible from the top. And that's where those satellite images can then capture the small details that give you a clue that you do have a fracture area deep down.
So hopefully we'd see this displacement here, and then we would go in and then drill a well and hopefully intersect this fracture, would then give us access to all the hot fluids that are down there in this geothermal reservoir. Well, sometimes in a geothermal system, we would like to have three things, right? We want heat, we want permeability, and we want water. Sometimes we don't have all three. Now we got volcanoes, it's great, we got all three right there. But sometimes, going to the interior of the US, we don't have all these three things. So being mankind, we said, if the geothermal isn't there naturally, let's create it. So there's big programs all throughout the world now on engineering geothermal systems. When you don't have either water or permeability, let's use water to inject it downhole, or let's create our own fracture system. The one thing you do need is heat. If you don't have heat, you're not going to do anything. But as we've seen, almost everywhere in the US and the world has enough heat if we just drill deep enough. So in these enhanced geothermal systems, we're basically mining thermal energy from hot, dry rock. And they have projects ongoing on that in Germany, in France, in Australia, and we have one in the US, in Nevada, at the Desert Peak. And basically what we're doing first is pumping water down and creating an artificial fracture system, just like Ken did over there, but we're trying to create a whole bunch of them by using techniques from the oil and gas industry, where you pump water down and crack the rock. And it's something like this, we need huge forces down there, because this is an example of a fractured granitic rock. Now the question is, okay, we go down there when we create these fractures, and we want geothermal systems to produce electricity for tens of years. I mean, the Geysers geothermal system in Northern California has been operating for over 40 years. So here we are trying to flow these hot fluids through these newly created fractures. So we have two challenges. The first one we just talked about. Can we create a permeable 3D fracture system for which we can circulate fluids? The second aspect is, once we've created that fracture system and we start circulating water through it, these fractures have never seen water before. Are the fractures going to be affected by the flow of water past them? And that's something that we're exploring in the laboratory with a series of laboratory experiments. And what we found is that actually fluid flow through these fresh fractures actually changes the fracture permeability. And so it's something we've got to have a good handle on as we start developing these EGS systems. We take a core like this or this, and what we do is we jacket it. We put it in a high pressure sleeve. And then when you put it together, you start flowing fluids through this rock. You can barely see it. And you look at how the fracture changes as you change the physical and chemical conditions of the fluid. And what we've seen is we characterize the surface of this fracture before and after. And if you come up here afterwards and you feel this fracture surface, it's not smooth. It's not like you're flowing water through a smooth surface. If you look at take a profile of the surface, like we do, and make maps of it, you can see it's got hills and valleys, and this is highly blown up, highly vertically exaggerated. But you can imagine being a particle of water trying to pass through this. These are the hills and valleys. You're going to be taking a path like this. And we modeled the fluid flow through this rock. That's exactly what it looks like. If you look at the flow going past this surface of the rock, you can see it channels. It's not constant throughout the surface of the rock. That's important to us, because water is the heat carrier. If the water doesn't effectively touch all the surfaces of the rock, it's not going to pick up all the heat. And that's why we care about flow through rocks. Here an example where actual flow through the rock has actually increased the permeability. If you look at this, this is a map of the aperture or the topography on the surface. The black spaces are the high spaces, and the white colors It's where it's low, when the fluid is flowing. And you see, after we flowed fluid through here for a little while, we've got some open space, so we're creating permeability, which is a good thing, and because it increases the heat transfer area. That's the type of work we're doing now, because we think the future of geothermal energy is these are enhanced geothermal systems, where we can create a geothermal system wherever we want it if the heat is there. Why are we pursuing this so vigorously? It's because geothermal energy can have a huge impact on our energy future. There was a recent study by MIT that took all the heat, the thermal heat that was stored in the earth between 3 and 10 kilometers. And they said if you took all that heat, we could supply the US energy needs for over 100,000 years. Now, that's a huge amount of energy. Now, obviously, we're not probably going to be able to get all that energy out. We don't want to because we want to cool the crust. But if we get just a small fraction of it out, we can have a huge impact on our energy. It's a great energy source. And right now, we use only just a small fraction of it. There are other ways we can use geothermal energy. As we've seen, the temperatures are higher on the west coast of the US. And we can get the high temperatures if we drill deeper on the east. But we don't even have to drill very deep to actually use geothermal energy. And that's through direct use. We don't have to create electricity. There's a lot of places on the earth where we can just use the hot water. And there are many places on the earth where we just pump up the hot water and use it to heat greenhouses. There's tilapia farms, fish farms, they grow better in the hot water. And what's really fun is they had so many waste products in the fish farm, they started having an alligator or crocodile farm right next to it to eat all the waste. And that's now a tourist attraction. There's a lot of district heating systems. In Boise, Idaho, and other places in the US, they actually take the hot water and pump it through their buildings to heat their buildings. And they pump it underneath their sidewalks to clear the snow and ice off their sidewalks. There's all different ways you can use it. And even though you're not creating electricity, what you're doing is you're displacing the use of other energy forms. So instead of using oil to heat your house or natural gas to heat your house, use geothermal energy and save all that oil and the fossil fuels that we need for gas and other things. Another way we can use the earth and the earth's heat is geothermal heat pumps. And this is something that can be put in a single home or in office complexes or a city. It's entirely modular. You're taking advantage of the fact that just a few meters below the Earth's surface, no matter where you are on the Earth, it's almost a constant temperature. Now compare that to the atmosphere, where you've got high temperatures and low pressures depending on the sun. We're taking the advantage of that difference in temperature. Drill a well down 100 to 400 feet below your house, and in the summer, you would take your hot water, pump it downhole, and it cools off. And then you pump that cool water up to your house and use it to cool your house. Now in the winter, when it's hot, when it's really cold outside, well, then just take the cold water, pump it downhole, and it'll heat up. And you bring the heat up to heat your house. So it's a whole different way to use the earth to displace the use of fossil fuels. And when you look at the impact on greenhouse gas emissions, by one person doing that, it's equivalent to taking 2 cars off the road or planting an acre of trees. So it is actually good for the environment. Now, I think that in the press, you probably hear more about wind and solar energy than you do geothermal energy. And I hope with this talk you may walk away thinking about geothermal energy as one of the big 3 in renewables. But I want to impress upon you that the US right now uses more geothermal energy than wind or solar. It is the main renewable energy resource being used right now. And you can tell we've got a lot more resource to take advantage of in the future. In California, we're the leaders in the nation on geothermal energy use. 5% of our electricity comes from geothermal energy, and there's tons more potential. In fact, I'm not sure if you know it, but just like 70 miles north of here, north of San Francisco, we have one of the biggest geothermal power plant in the world. It's called the Geysers. It was misnamed. Somebody explored it and saw hot water and called it. There's actually no geysers there, but there's a lot of hot water. It's the largest geothermal power plant in the world. It produces about 750 megawatts. It's enough to power all of San Francisco. We've got tons of resources. They're developing in Northeast California, in the Imperial Valley. We have tremendous resources in California. And actually, we dwarf other states in energy usage. And I see for the future, there's tons more geothermal power plants being constructed right now in California. And that's a good thing, because there's another reason why it's good to use geothermal energy, as Ken will show.
One of the things you need to think about is the byproducts. Geothermal can make electricity just the same as fossil fuels can make electricity. We have lots of coal, we can burn that coal and make electricity. What you look at then is what are the byproducts that are coming from it. When you have a coal-fired plant that's producing that electricity, then the byproduct of it versus a geothermal plant, I think I'd like to live next to the geothermal plant because water doesn't harm our atmosphere, whereas putting more carbon in may have some detrimental effects.
Excellent. And people do live right next to geothermal power plants. And this picture shows the geothermal power plants are right in the middle of all the great agricultural regions down in Southern California. There's some good pictures that illustrate the benefits of geothermal energy. And that's if we go to Iceland. Back in 1932, Reykjavik in Iceland, a town in Iceland, it was a town of 28,000 people, heated all their homes with fossil fuels, imported fossil fuels too. And this is what the atmosphere looked like. Now think of it. Livermore is actually 3 times the population of Reykjavik back then. This is what Reykjavik looks like today because they use geothermal for almost all their heating uses. They're using it to power industry, whatever, but it has a huge impact on the environment. This is one of the best examples I know of that. Not only are we talking about soot and things like that, but you know there's a big problem with global climate change and greenhouse gas emissions. And if we compare some of the greenhouse gas emissions like CO2, here's the CO2 emissions for geothermal. You don't have to worry about the absolute numbers, but look how it's compared to the other fossil fuels, natural gas, oil, and coal. Basically, geothermal has 90 to 95% fewer greenhouse gas emissions than coal. And as Ken pointed out, when you drive up past a power plant and you see these plumes coming out of the power plant, remember, they're steam, they're not smoke and soot. So that makes, I think, it's a wonderful, clean, green, and renewable resource, especially if we manage the reservoir properly. Well, when you look at the Earth, I look at this picture from space, and it looks like a very cold place. But I hope after today, when you look at the Earth, you think there's a lot of heat in the Earth, and there's heat we can use for direct use, we can use it for heating, we can produce electricity, and it's clean, it's green, and it's renewable. And I think it's good. Geothermal energy is going to play a big part, along with the other renewables, in our energy future. And I hope when you graduate and you become scientists and engineers, that you'll be one of the people to help make this happen. So I'd like to thank you very much.